All right, let's get started. Homework 1 is available on the course website. It's due next Tuesday. Right? It's on basically a couple of problems on FFT and one problem on dynamic programming, which we'll cover today and next few lectures. So I assume most of you have seen dynamic programming in at least some baby form before. Some of you probably haven't, right? If you've taken 374 or some other basic algorithms course, you probably saw dynamic programming. Is there anyone here who has not seen dynamic programming before? It's okay, it's fine. Right? Yeah? No? Everybody has seen dynamic programming before, I guess, yeah? Okay, but even though many of you have seen dynamic programming, we're going to spend some time on it, right? Basically to review and to sort of give a more advanced perspective on dynamic programming and some applications. It's perhaps one of the most powerful algorithmic design techniques in addition to other techniques, right? So it's important to understand it well and see some interesting applications of it. Okay, so it's a technique that is also a bit hard to teach for me because it's always it's not an easy thing for students to absorb. So we'll seeing it again, maybe if you've seen it before, seeing it again in a different way or in a second time may be actually a good thing in any case because it's a very nice, important technique. Okay, so we all know the notion of a reduction. What's a reduction? It's simply trying to convert one problem into another problem, and we kind of implicitly use it all the time, right? If you know how to solve sorting, we try to use sorting to solve something else, or like you saw in homework 0, you know how to solve shortest path, and you don't even need to know the algorithm for shortest path, but you can convert something which looks like a shortest path into a shortest path problem, right? So reductions are sort of very important and very basic and intuitive, and recursion is one particular type of reduction where we reduce the problem to a smaller instance of itself. The advantage of recursion is that you don't have to know any other problem, right? In reductions, typically you need to know that something else needs to be solved efficiently, and then you can reduce your problem to that problem, right? While in recursion, essentially it's a technique which is basically to take a problem and say, look, I can solve it by solving smaller instances of itself, and that's that's even better because you don't have to look elsewhere, right? But to apply recursion, you need to understand some basic structure of the problem so that you can actually do the reduction to itself. So it's there are many techniques which are built on recursion. One is the most easy thing is what's called tail recursion. Even though it's given a special name, it's basically you reduce a problem to just one smaller instance of itself. In some sense, if it's the simplest form of recursion, then you can almost forget about the recursion and kind of many times greedy algorithms and other things can be thought of as basically tail recursion, right? So there's only one instance. So you see, the reason why we give it a name is because it occurs frequently in algorithms. So we think of it as one application of recursion. We have also seen divide and conquer, right? Like FFT was a divide and conquer problem. One of the first algorithms you see is merge sort for sorting an integers, right? That's a divide and conquer. You take an array, you sort it into two, you break it into two, sort them, and then merge them, right? So divide and conquer is also a very powerful technique. It's, as we saw, for example, in FFT, we there's math, but then we do divide and conquer, right? So divide and conquer typically, it's not always, is typically a technique to speed up an algorithm rather than develop an algorithm for an efficient algorithm that you couldn't do otherwise, okay? For example, take multiplying two polynomials, right? It's easy to see that you can do it in n squared time. So the thing which we did was, okay, you can actually do it much faster. Same with sorting, right? You can actually sort n numbers easily in n squared time. The fact that you can do it in n log n time using divide and conquer is not obvious, right? So typically, not always, divide and conquer is a technique that allows you to take a problem and speed up the solution compared to the obvious polynomial time algorithm. or some other class, right? So it's okay. Well, in some sense, brute force search is the obvious technique too, right? If you see many problems that you will encounter can be solved by an exponential time by just trying all possible solutions. Why is that? Because the number of solutions for many problems you see in practice is only exponential in the input size, so you can try all of them and find one of them, right? So you can improve brute force search by thinking of it as backtrack search. It will come back to this as a heuristic later on, but that's also can be thought of as recursion. But dynamic programming is a sort of is a technique based on recursion, but by cleverly memoizing the recursion. That is, you take the recursion and it doesn't create problems that are independent like divide and conquer does. So it creates problems that the recursion creates several instances which kind of have some dependence between them. Okay, and then if you are clever about how you remove the dependence by either memoizing it or thinking of it in a slightly different way, you will get an efficient algorithm. So it's a very powerful technique, but it sort of has this difficulty in advanced applications of it somewhere straddles the boundary between efficiency and brute force, right? So that's why it's a little difficult, right? It sort of seems like, okay, when do I apply it? How do I apply it? For what problems does dynamic programming apply to actually get an efficient algorithm? That is a little, when you see a brand new problem, if you see a problem that is very easy to relate to some existing problem, which is what you will see mostly in homework and exams, it's okay, right? You'll kind of get the hang of it. When you go into more advanced topics, when you see a brand new problem and you're thinking, does it have an efficient algorithm? Does dynamic programming apply? And that is a little bit harder, but we hope that you're seeing it second time and you see some advanced examples and we'll give it a slightly different perspective, and hopefully that'll become a little bit clearer. Okay, so let's do, it's some of you have seen this material before, but it's good to review. So let's take any recursive program or algorithm, right? It looks something like this, right? It's some foo, you start with some instance x, and if it's a base case, you solve it simply, right? If it's not a base case, then you do some work and you say, okay, I'm going to call recursively myself on some smaller problem, right? Maybe you'll call it multiple times, right? Not once. I'll say, okay, I'll call foo x1 and then on something, foo x2, then foo x3. And then you, from all the solutions for these 3 or 4 or how many ever recursive calls to smaller instances, you put together the solution for x, right? That's typically some recursive thing, right? So there are 2 important objects we need to understand whenever you have a recursion, right? One is, if you think of implementing the recursion, how does it look like, right? It will create what's called a recursion tree, right? You can create a tree, right? You put x, what does x do? It creates 3 children, right? It spawns 3 calls, right? And what do? They spawn more calls, right? Okay. Now that's the obvious recursion tree, and we will look at that. But the other thing that we also need to look at is, when this recursion tree, look at the recursion tree, some of the problems will recur in many places, right? You will create the same problem in the tree in different places. So you can create actually a different graph, which is actually going to be a DAG, a directed graph, directed acyclic graph, where you say, I don't want multiple copies of these separate problems, I only want one copy of it, okay? So given a recursion, there are 2 objects one needs to pay attention to. The recursion tree, if you just implement it directly as a recursion, the computation time will depend on the size of the recursion tree, okay? If you implement it as, if you actually pay attention and say, okay, look, I'm recomputing the same thing again and again, and not do that, you will actually create what's called a dependency graph, okay, or a DAG, we'll see, okay? That's abstract. Let's see a very simple example, which is the standard thing, but it's always good to use a simplest example. Most of you have heard of what's called the Fibonacci numbers, right? So what is the Fibonacci number? You know, it's a number defined by this recurrence, right? F of n is f of n minus 1 plus f of n minus 2 with the base case of f of 0 is 0, f of 1 equal to 1. Okay. Why is this interesting? Fibonacci numbers, for whatever reason, this recurrence occurs in life, it seems, right? You know, it is a very strange, simple recurrence, and there are many reasons why this recurrence is interesting, both mathematically and in nature. Apparently, there are many patterns in nature where this recurrence happens, and so it has many mathematical properties also. So in fact, you know, there is a closed form solution for f of n, and it is given by this, right? It is phi to the n minus 1 minus phi to the n divided by square root of 5, where phi is the golden ratio. Okay. Okay, you can figure this out by the recursion, I mean, how to solve recurrences. What is interesting is that even though this is completely defined on integers, right? F of n is an integer by this recurrence, somehow, you know, you get irrational numbers when you write a closed form solution. It's the root of some problem, right? And then how fast is the Fibonacci number growing? You know, as n tends to infinity, the ratio of, from this formula you can figure out that the ratio of fn plus 1 by fn is phi. So it is growing pretty fast, right? Roughly f of n will be phi to the n, right? Phi is something bigger than 1, so it's growing exponentially, right? Even though you start with a very simple recurrence, the numbers are growing very fast. Okay? Okay, so that's just a definition of Fibonacci numbers, and maybe, you know, somebody will say, you know, compute the nth, you know, write a program to compute the nth Fibonacci number for me. Right? You say, you know, I give you 10 and you should give me f of 10. Okay? Make sense? Right? You know, how will you do that? Right? Okay, so, you know, you can simply write the recursive code by the definition. You can say, you know, there is a simple recursion. If n is equal to 0, return 0. If n equal to 1, return 1, else return blah. Right? The definition of the recursion. Right? Okay. So what happens if you do that? Right? So, well, you know, what is the running time of this algorithm? Right? It is computing f of n. As you can see, you're following the definition. How long does it take? Right? Well, let's say, you know, T of n is the number of additions, right? Let's not worry about the bit precision because that is actually blowing up. But say, you know, how many additions do we need to do, right? Well, let's call that T of n, right? Well, you know, what is it? T of n is, by the recursion, it's T of n minus 1 plus T of n minus 2 plus 1 addition, right? Okay? And T of 0 and T of 1 is 0, so we don't do it, right? So this recursion is roughly the same, looks like f of n, right? Because we are following Fibonacci recursion, right? So the T of n will be roughly basically f of n, right? Okay? You're spending the time that this recursion takes to compute f of n is basically roughly f of n itself. But how big is f of n? We know, right? F of n is basically phi to the n roughly, right? So this algorithm will take exponential time in n, right? If I give f of 10, it is going to take a long time, okay? You can run it actually. You can write this code down. It's very easy, right? You know, 5 lines. It will take forever to finish, right? Well, why is that, right? You know, let's see why it does that, right? You know, it's very easy to see why it does that, right? You know, so you look at what is the recursion doing, right? You know, you say, okay, I start with 5. It'll make 2 calls, right? It'll say, okay, I'm going to call myself with 4 and 3, right? And then what does 4 do? Okay, it says, okay, I'm going to do 3 and 2, right? And 3 is going to call 2 and 1, right? And 3 again is going to call 2 and 1, and you can see, right? You know, so you can see here that, you know, we are repeating work, right? So 2 is here, 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 3 is here, right? 1 will occur many times and so on, right? So on the other hand, what will, so for every recursion, you can create this recursion tree. It's a tree because they don't, right? But we also want to think of the recursion, a dependency graph associated with this starting the recursion on a particular instance, right? There, what we want to do is say, no, I only want one node per distinct problem that I create, okay? All right. So okay, you know, what should I have in that? How many? If I start with a fib of 5, what are the problems I will get? 5, 4, 3, 2, 1, 0. Right. That's all I'll get. So it's easy to visualize that. So okay, I'm going to draw a different graph where I have 1, 0, 1. 0. I mean the 3, 4, and 5. Okay. I only want one node per distinct sub-problem that was generated. And now I'm going to draw an edge from a particular problem to the problems that it calls. Right? So it depends on, right? Okay? So it's a directed graph. So what is 5 going to call? So I put an edge, you know, the convention, you can either put the arc from 5 to 4 or 4 to 5, right? Depends on how you want to think about it. I want to put it the other way, okay, just because there is a nice thing. So think of this, you know, what this says is that 5 cannot be done if 3 and 4 are not done, right? That's one way. I mean, you can put the arcs the other way too. It's just an interpretation, right? Okay, so what about 3, you know, you create these arcs, and 4 has an arc from this, you know, it's the obvious one, right? You know, and 0 has, no, this doesn't have an arc because it's a base case, and, okay, makes sense, right? You know, okay, this is basically the, okay, I claim that this has to be a cyclic graph. There cannot be cycles in this. Why? Sorry?
The recursion only called one way and not the other.
If there is a cycle in that, the recursion will not terminate, right? Okay? That's the whole point of recursion, right? What does a recursion do? It creates problems which are smaller than itself. Okay? So there is a natural ordering on the problems that is happening, right? If there is a cycle in this graph, that means there is a dependency cycle, then the recursion will not terminate. Okay? Does it make sense? Yeah? Okay. So you can see that the size of this graph, the size of the running time of this algorithm depends exponentially on n, which means that the size of this tree is exponential in n, while the size of this graph is only linear in n, right? There are only n problems because that's what we are doing, right? But this is creating many times, right? So, okay. So, you know, once we, you know, so there is no reason to recompute all these things. Once you know this, right? Suppose we knew this graph, we can just compute 5 using just this graph, right? How will you compute fib of 5 using this graph? We'll just topologically sort this. That is, we order them from no dependency, the sources to the sinks, and then just say, okay, to compute 2, I just compute the sum of this and so on, right? Alternatively, even if you didn't see that, you know, there is a simple iterative algorithm, right, to compute, which is basically what we are imagining the dependency graph and computing it essentially bottom up, right? Right? What is that? You know, you say, okay, you know, I allocate an array of size n, and I say, okay, I know the base cases, then from I equal to 2 to n, I'll compute f of I is f of I minus 1 plus f of I minus 2. So running time of this is only n. Okay? So what is this doing? This is very simple. This is n additions. That is just basically, we are not recomputing the same problems again and again by remembering the values of the things that we have computed before. Right? Every recursive algorithm, doesn't matter what its structure, can be memoized. This is called memoization. What does it mean, memoization? To avoid recomputing the problem again and again, we have to store its value, right? Otherwise, you won't remember it, right? You have to regenerate the instance, okay? So every recursive problem can be memoized, right? Okay? So that's, it doesn't have to have any meaning. I mean, you start with any recursive algorithm, right? You know, you can, okay. So now how do we do the memoization? What does it mean to memoize, right? Okay. So if you knew the structure of the problem, like Fibonacci numbers, we can, you know, it's so easy that you say, okay, I know what the subproblems look like, right? They are 1, 2, 3 up to n, so I can actually understand the structure and create an explicit data structure to do it, right? It's very simple. It's too simple at some level. Don't be misled by the simplicity of that. Well, in some sense, every recursion can be automatically memoized if you're into programming languages or, you're, right, you can imagine that, you don't even want to think, right? You say, okay, whenever I generate a problem, I just will store store that instance in some place, and if I computed the value, I'll store the value along with it. And when I create a new instance, I say, did I compute it before? I look up some table, some data structure, see if I've already done that, and then take the value if it is there, otherwise I just recompute it, okay? So you can do it in some sense, how do I automatically take a recursion and avoid recomputation? By storing values, right? How do we store values? Well, there are roughly two ways. One is I don't want to think, in which case I have to use some data structure, right, which is oblivious. So for example, I'll use a dictionary data structure, right, and I say, okay, whenever I generate a problem, I'll throw into this data structure, which will keep track for me this instance and its value, and when I want to query, I say, okay, now when I get a new instance, I say, have I computed it previously? I check in this data structure, is it there? If it is there, I return the value. If it is not there, I have to do the computation, right? So you can do it automatically, right? That's what's called basically a top-down automatic memoization. You just use a data structure like a dictionary and so, right? What is the other way? Other way is, this is the top-down way, right? I don't know what I'm doing, right? I'm just basically, so this is, so here is one way of doing it, right? So here I know a priori that, there are n values, so I'm allocating an array of size n, right? So this is basically an explicit way of memoizing, and in the implicit way, where I don't understand the structure of the problem, I just use some dictionary data structure. Okay, I don't know what is going on. I don't understand the problem at all, right? So I just use a dictionary. I don't understand what the running time will be in that case. Okay, so you can do it automatically, right? Okay, so this is a very simple technique. There are some advantages. We'll not worry about that. But what is dynamic programming, right? So every recursion, blindly, okay, without thinking, if you have a recursive algorithm, you can memoize it, okay? Okay, now that's not dynamic programming, okay? The point of dynamic programming is that when you see a problem, right, if I did the memoization, what happens to it, right? What is, we have to understand what is the running time of that algorithm by understanding what is the structure of the problems that we are generating, okay? And that dynamic programming is a recursion that if you memoize it properly will lead to an efficient algorithm, okay? So recursion being memoized is a dumb technique that anybody can use, right? So dynamic programming is the art or the skill of recognizing when one can get an efficient algorithm by taking a recursive algorithm and memoizing it, okay? Not all recursions for the same problem lead to an efficient algorithm when they are memoized, right? So the key questions that we need to understand when you are applying dynamic programming is the following. So first, you can do the following, right? You come up with a recursive algorithm, and then, we have to understand, if I memoize it, will it lead to an efficient algorithm? Okay? That's one basic thing, right? I have a recursive algorithm, right? And then I think, what happens if I actually memoize it, right? Does it actually going to give me, is it going to give me an efficient algorithm, or is it going to give me not an efficient algorithm? So what is the key to understanding that? The key to understanding that is the size of the dependency graph as a function of the size of the input. For the Fibonacci numbers, we easily could see that the size of the graph was polynomial in the input size, right? While for some other problems it won't be obvious, so we have to understand that, right? That's the most basic thing we have to be able to do. Given a recursion, can we figure out what the structure of the problems is, right? So that's not all, right? If that was all dynamic programming, then we'll be done. The key question that, whenever we want to design an algorithm is, if I give you a problem, how do I know that there exists an efficient way there is a dynamic programming based algorithm that if there's a recursion that if I memoize, I'll get an efficient algorithm. That is the main thing that we will want you to get at, right? When you see a new problem, you say, this looks like a dynamic programming problem. How do we figure that out, right? And then, the last part which we will see, which we typically don't see in the basic algorithm course, is how do we further optimize? Once we have the most basic understanding of the problem structure and we can get a polynomial time algorithm, how do we make it faster? By using data structures or some other techniques that we'll discuss. Okay? So the key, so this is one skill, this is the second skill, this is the last skill, right? We need to make sense of these three pieces. Okay, so let's do the first skill, right? The first skill is actually, this edit distance is a very standard problem, but it's a standard problem, but it is a very canonical problem, many applications, especially in bioinformatics. If you do any kind of bioinformatics, this is the bread and butter, right? And then it also is a very illustrative thing. So even though you've seen it before, we'll think about it slightly differently. So what is the edit distance? I have two strings, x and y, think of words, and I want to understand how different are they, right? What does it mean to understand how different are they? You want to say, I want to create some measure or some distance between two strings and saying, oh, this is very different from that, right? Or this is actually the same string as that, right? So how do you do that? There are many ways of doing it. One way of defining a distance between two words or two strings is how many operations do I need to do to convert this string to the other string, right? So what are the operations? Well, what are natural, as the name suggests, in the edit distance, you say, okay, I want to edit this string character by character, right? What are the operations I'm allowed to do? I can take out one character, that's called deletion. I can insert a character, that's called insertion. Or I can swap a character. And I say, I want to replace this character by another character. What is the minimum number of operations I need to convert this string to the other string, right? That's called edit distance. Okay? And it's, so here is an example, how do you take food and money? You say, okay, this is one way of doing it, right? You say, okay, I'm going to change F to M, right? And then change O to, what did I do here? I insert N and then change O to E and then D to Y, right? So that's, 4 steps. So that's the edit distance in the, but that's may not be the smallest way of doing, right? So what is the smallest number of edits you need to do, right? So this is very easy, maybe, if you, not so easy, right? Even for 5-letter words, it's not easy to compute this, right? It says unless you think systematically, right? So this is a problem, a simple classical problem, where the existence of a polynomial time algorithm is not obvious. Okay? I want us to think about that. I give you this problem, right? You have never seen this before. It's not at all obvious that there exists an efficient algorithm for this problem. Okay? You cannot see it, right? You can, if you try, basic techniques like, it's not obvious at all that this exhibits a efficient algorithm, right? But we'll see, as you know, you've probably seen it. So there is a different way of thinking about edit distance. The standard definition is actually a little bit hard to think about it. A more natural, after you spend some time, a more natural way of thinking about edit distance is to say, okay, how do I go from this word to that word? It's useful to think about it as aligning the two strings in some fashion, right? But what's an alignment? You say, okay, look, I'm going to put the first string on top, the second string on bottom, okay? And what is an alignment? I match up basically letter by letter and I allow some blanks as well, okay? So if I have a blank is matched to this, that means that I'm going to like insert this, right? If I have two characters which are the same, then I don't have to do anything. If I have two different characters, that means, I'm going to replace that by this, okay? If I have a character here and a blank here, that means I'm going to delete it, right? So one can actually it's not very hard to see, I will not go through the formal details, that computing the edit distance is the same as computing an alignment between the top string and the bottom string. And what is the cost of the alignment? The cost of the alignment is the number of characters where the alignment differs. Okay? So each time in F and M I have to pay 1 because I'm swapping that. This I don't have to pay. Here I have to pay 1 because I have to swap this. And here I have to pay 1 because I'm inserting. And I may have to delete, in which case I have to pay 1. Okay? So the cost of edit distance is the same as this alignment problem. You have to see that, but I'm not going to go through the proof. It's not very hard. Okay? Alright? Okay. Now the problem becomes, how do you compute given two words, the edit distance between them is an alignment of the smallest cost, right? So how do we solve this problem? Okay. Okay, the key step, is at least you have to, let's think of a recursive algorithm for this problem. Okay. So, and I mean, since many of you have seen it, I won't go through the exercise of thinking about it online. You can try the most basic recursion by thinking of the alignment and saying, okay, what does it mean to align the string x and y together, right? Well, if you try recursion, you want to make it simpler somehow, right? So we try to do it incrementally, right? Let's think of the string x as alpha followed by a single character x, right? The string y as beta followed by a string character y, okay? Now I want to align x and y. Think of what are the possible alignments, right? Well, it can look like this, right? I align x with y and then somehow map alpha to beta, or I map alpha to beta y and I basically delete x, or I can insert y and somehow align alpha x to beta. So those are the only three possibilities, right? Yeah? Okay? So, okay. Now, suppose, if I decide to do this, then under the assumption that I align x to y, I should obviously, if this is the one I'm going to follow, I have to optimize the best way to align alpha with beta, right? I can't do something suboptimal with alpha and beta, right? So I want to claim that the best edit distance between x and y is, well, you decide which of these cases you want to go through, and then recursively find the best way to align these smaller problems. Okay? Yeah? So there are three possible cases. I don't know which of this is actually true, right? But these are the only three possible cases, right? That I align x to y, or I delete x, or I insert y, right? And then once I figure that out, I have to recurse on the smaller problem, because finding the best edit distance between x and y, where I align the small x to small y, is to pay 1 if they are different, and then optimally align alpha and beta, right? Okay, how do you prove that this is correct? You have to prove it by induction, basically. Okay, it's not hard to prove this, but you have to prove it by induction that this is a correct recursion for this, right? Okay, it's so obvious that you don't have to think much about it, right? That once you figure that this is the decomposition, then figuring this out is not hard. Okay, that is correctness of this. Okay, so at least now we have a recursive algorithm, right? Okay, so now we can just run it, right? Okay, now what is the running time of this algorithm, right? If I just run this algorithm, what happens? Well, it will generate a big recursion tree, right? Okay, it's not hard to convince yourself that the size of the recursion tree that it generates, if I take two strings of say n and m, is exponential in n, basically. Okay, so so then we can ask the next question: what happens if you actually memoize the recursion? We don't do the recursion tree, but we actually do the dependency graph. Okay, how big is a dependency graph? How do you understand that? Right? Okay, so to understand that, so this is the recursive code, right? You can run this, right? It's correct. What is the base case? Let's understand the base case, right? What happens in the base case? Before we go on to the memoizing, what we didn't understand the base case here. When can we not do this? We can always, yeah. Yeah, if one of them is empty string, I can't do this, right? Because x is not, I can't even write one character in x, right? If x is empty string, what's the right thing to do? Say one of them is empty string. The optimal solution is to insert essentially all of y, right? So if one of them is empty, we know the optimal solution is the length of the other string, right? So those are the base cases, right? If one of them is empty, then the right answer is the length of the other string. Otherwise, you can do this recursion, right? So the only question is how long will this recursion tree will take a long time. So we want to understand what happens if I memorize the recursion, right? Okay, what does it mean that what happens if I memorize the recursion? I want to understand if I start with input of size n and m, what is the structure of all the problems that is being generated, right? Okay, how do we know that? So let's, you play with it, you try an example, right? So suppose, I'm trying to align this. What happens when I do that, right? So I start with this. What are the three cases that will generate? Okay. So initially I start with these two, right? Deed and dread, right? What are the three possibilities it will generate? Three problems it will generate, right? Okay. Okay, what does it generate? So one is the D and D are aligned, and then I have to do D, DEE and DREA, right? What is the other possibility? That I'm not sticking to this one, right? I basically inserted D on the second thing, and the third possibility is what? Okay, all right, and then I can, this again generates 3, this again generates 3, this again generates 3, right? Okay, it's a lot of problems it will generate. But you realize that, let's see, one of the cases, just to understand this, one of the cases here, what is one of the cases here? I basically delete D, right? And so one of the cases here will be DEE and DREA, right? Okay? Do you see that? Okay, so that is the same as this, right? Okay. We don't want that, right? We want to only remember the thing. Okay, what is the structure of the problems that I'm generating through this, right? Do you have any understanding of it? Right? As this thing keeps going, what are the different types of problems I'm generating? Is there a structure to it? It's a 2D array, but in terms of the strings, I claim that if you look at any problem, it's a prefix of the first string and a prefix of the second string, right? So any problem that I generate is a prefix of the first string and a prefix of the second string, right? So how many such problems are there? Right? There are only n, if the n is the size of the first string and m is the size of the second string, the number of prefixes of the first string is n and the number of prefixes of the second string is m, so there are only nm different problems that I'm generating, right? So I know a priori that the size of this graph is only going to be nm, right? Where I only put one node per different problem, right? So that comes by just looking at the recursion and understanding that I'm not generating too many different problems, okay? So then we can memorize this recursion, right? Now we already understand what is the sub-problem that we would generate. It is a prefix of the first string and a prefix of the second string, right? So let's give it a name so that it's easy to remember, and we'll think of it not as a prefixes, but we'll say, aha, the problems I'm generating are of the form I and j, where 1 to I is a prefix of the first string and 1 to j is a prefix of the second string, right? So we'll say, okay, what is then, we can easily think of these as the sub-problems, right? Opt ij for 1 less than I less than n and 1 less than j less than m are only problems that I will generate when I solve the original problem with opt nm, right? So, and then we also know from this, the same recursion, that how do I compute opt ij? It is xi, if xi and yj are equal, we recurse, if you align xi with yj, then we pay the cost here. It is a Boolean variable, okay, that I'm using some compact notation. This is just, which programming language is this? I forget. In an old programming language, this was a notation to say it's 1 if that is equal, 0 otherwise, right? It's some, so anyway, just to be compact, right, instead of writing if. So it's opt I minus 1, j minus 1 plus 1 if they're not equal, and 0 otherwise. No, this should be, yeah, this should be not equal, right? Okay. And we have this base cases, and we then don't have to do the recursion, right? We can just avoid the recursion and do the computation using this subproblems, right? Okay, I'll skip this. Let me look at the dependency graph of this, right? So what is the dependency graph of this problem? Well, what are the problems, right? Opt ij for I, in fact, technically it's 0 to n and to be, right? The graph looks like this, right? Does it make sense that the graph looks like this? Right? We can think of opt ij as a rectangular array, right? Okay, opt ij is, this is the, so maybe I might confuse the indices. What is the length? A is of length m and B is of length n, right? So the dependency graph for the edit distance problem has one node per each subproblem, right? Okay, and so that's what we drew, right? And what does it depend on? Ij depends on what? It depends on I minus 1, j minus 1, I j minus 1, and j I minus 1, right? So there are only 3 arcs. And how do you compute the value of this? You compute the value by looking at these 3 values, right? Okay, and what do you want to compute? This guy, right? Okay, so what happened here, right? We took a reasonably simple recursion and we observed that if you understand the structure of the problems, there are only polynomial number of subproblems, right? And then you said, we can remove the recursion if you want, right? And compute this value. You take this dependency graph. We understood the structure of the subproblems. We said, then we can put this dependency graph, and then we can compute the values we want, right? Okay? Okay. And you can do this computation in many different ways, right? Ultimately, what do you want? You want the value of here, right? What do you know? These are the base cases. If it is 0 here, you know all the values here, and you know all the values here. How do you compute the value of this one? Which way should you evaluate this? How do you compute the value of this? So which order should you evaluate these problems? Okay? From a graph terminology, this is what? This is a sink, right? And this is so. So we know the values of this, we know the values of this. How should I order this DAG computation so that I get the value of this? Sorry? Breadth first search. So this is a DAG, right? Every DAG has some nice property. What does it have? Yeah? So it's a topological sort, right? So I can basically sort, that means there is a way to order the nodes of a DAG in such a way that all the guys that I depend on come before me, right? So in some sense, this guy depends on all of this, right? If you take the transitive closure. So which way should I do? In fact, any topological sort of this DAG will do, right? So one way to do it is the following. You compute, we already know the values of this. So you compute the values of all these guys. Is that okay? Because they all, from the DAG, you can see that all these guys can be computed if you have the values here. Then you can compute this, you can compute this, you can compute this, and you get here. That's one topological sort of this DAG, right? What is another topological sort? You do this, you do this, you do this, you do this in column order. That's also fine, right? Okay. What is another thing? I don't care. I say, okay, I go here, then I do this, I do some funky thing, right? That's also okay, right? So what is you have flexibility, right? So you can do optimizations with that, okay? What is one optimization you can do? Okay, so before we do that, what is the running time of this algorithm? How do you understand the running time of this algorithm? Okay, first, how are we doing the computation? By saying, we are going to allocate an array for all these values because I have to store them, right? Okay, I store, how much space does that take? M times n, right? Because there are a number of problems, right? If I have the number of problems, that gives me roughly how much I have to store. Depending on the problem, I might have to store one number, I might have to store some string, I might have to store some big structure. So you have to think about what is it that I'm storing in this, right? Okay, so you store that, and what is the time to compute one value here? It only takes constant time if I had the values for the other things, because it's only depending on what? 3 things, right? So evaluating the number takes only constant time if I had all the other previous values. So the running time will be mn, because it's how many problems I'm evaluating times how much work it takes, right? Right? So that's just roughly it, right? But then you have to pay attention to a precise, when you actually give an algorithm, one high level thing you can say is, take this dependency graph, I understand the structure of it, do a topological sort, done. That's fine, right? At high level that's fine, but typically you also want to give a specific order in which you want to evaluate this so that you actually can optimize and stuff, okay? Okay, so this is an easy problem in the following sense, right? You started with an obvious recursion and you just understood the structure of the subproblems, and then you realize that it's polynomial size, and then you're done, right? Okay, so this is not always going to be so easy, right? Now, one simple thing I will suggest, which you can, simple optimization that comes to mind when you actually see the structure of this thing is, do I need to store all the entries to get this final value? Why not, right? See, the obvious thing is, yeah. So to compute this, I need to know these 3 values, but how can I avoid storing all these guys, right? Okay, so one way is, you said, no, we can compute this by doing it row by row, right? So to evaluate these guys, I need to know all these guys, basically, right? So once I come to this 3rd row, do I need the top row? You realize that you don't, pictorially it's very easy to see, right? So when you come to the 3rd row, you don't need the top row, right? So when you come to the 4th row, you don't need the 2nd row. So if you do the row by row computation, you can only need to keep only 2 rows at a time. Okay. So that, if you implement it in the slightly clever, you have to just throw away the row and store the next row and so on. You only need 2 rows at a time. Okay. So you already saved space, right? The running time is still mn because you had to evaluate all these mn problems, but you don't have to store all the previous ones. You're reusing space. Okay. So that's an optimization, right? You could do the optimization only because you actually stared at this a little bit more than if you didn't think at all, right? Okay, should you do this row-wise or column-wise? Sorry? You could do it column-wise also, right? But then, you should pick the one which is smaller, right? If the row size is much bigger than the column size, you should do the columns. The column size is, it's an obvious optimization, right? So you can do optimizations once you understand the thing, but that's not the first goal. Your first goal is like, does dynamic programming apply to this, right? Okay, good. So here is the interesting question which comes up. What this recursion does is it only computes for you the value of the alignment, right? Okay, I want the alignment also, the solution. I'm only computing the value, right? How can you compute the actual alignment? Sorry? You want to do backtracking. Okay. What does it mean? Okay, so let's do a simple thing. How do I compute the how do I compute the value? Let's not try to be very efficient, right? What is the most obvious solution? That is, I want to compute the actual alignment which gives this value. How can I figure that out? That's the obvious thing, right? You say, okay, whenever I compute the value, I also keep track of a specific alignment that achieves that value, right? I store that alignment, right? Okay, can you tell me, if I knew the alignments here, how can I compute the optimum alignment that achieves this value here? What is the right alignment? How did we decide that this was, how did we compute this? We computed the optimum value as the best of these 3 cases, right? Each of those 3 cases is an alignment, right, actually. And we said this is the best alignment. See, let's go back to the recurrence, right? What is we saying, what is the base, what does it start with, right? We said, okay, if to align x and y, you try these 3 cases, and pick the best, right? Well, when we tried these three cases, we figured out which one is the best for us. But how do we figure out, I mean, when we do the bottom-up recursion, the computation, we already knew the best alignment for these sub-pieces, right? They are stored in us because we are storing them. And so we can figure out, along with the value, we can figure out which of these alignments is the right one. And we can store it in the IJ for the future guys, right? It's obvious at some level, right? We store the right alignment by whenever we compute the optimum value, we say, that is the decision I used, so that must be the right alignment. One right alignment, it could be multiple, right? There could be ties, but I store one right alignment, that's enough, right? So, okay, well, what happens if you do that? If you do that, it's a fine algorithm. The only problem is that, you're storing a lot of alignments, no? For each of the table, you store a lot of alignments. Okay, there's a small trick where you don't have to store the alignment. What should you store instead? Sorry? So I don't actually, finally, I only care about the alignment that achieves this value, right? I don't need to store all the intermediate alignments. Okay? So what I can do, instead of storing here the actual alignment, I just simply store a variable which says, how did I compute that value? Which of the three cases I actually used to get that value? Suppose I only store that information. Okay? Right, how did I get to that value? I only store a number between 1 and 3, right? Did I choose this case? Did I get this optimum value by going from this guy or this guy or this guy? Now, once I come back, compute this value and store those numbers, can I go back and compute the optimum alignment? Okay? You can, okay? So I'm not going to go through the details. So this is just another optimization. Instead of actually storing the full alignment at each of the sub-problems, I only store the decision I made to compute that value. Which case did I choose to optimize this? I store that, and once I store all those values from here, I can figure out, going backwards, the full alignment just for this guy. Okay? So the space will still remain Mn because I'm not storing the entire alignment. But one thing happens then. If I have to recreate the alignment, I cannot throw away information. I cannot save space. Right? If I have to recreate the alignment in addition to the value, if I throw out the array, then I cannot create the alignment. Okay? So that's a kind of a thing that we'll discuss in a couple of lectures from now. That's not easy. You cannot easily compute the alignment if you throw away information. Okay? So if you save space and make it linear in M and N, you cannot compute the actual alignment, you can only compute the optimum value. So can we get the best of both worlds? Can we actually compute the alignment? Well, that's non-trivial and we'll see a trick for that. Okay? That'll come later. Okay, but think about that a little later. Okay, here is an exercise for you. This is also just before we go to here is maybe we won't spend too much time on this because I want to cover one more thing. A sequence is called a palindrome. Everybody knows what a palindrome is. It's a string which reads the same from left to right and right to left. Okay. Here is numbers, right? This is a palindromic sequence. This a single letter is a palindromic sequence. I know this. What is this? How many people know this? This is my favorite one. Why? Yeah. So some of the Indians here would know it. It's actually a language in India that my wife speaks. I don't, right? So it's a South Indian language and it's a palindrome. Okay. So that's right. Okay. So they're all palindromes. So here is the problem. I give you a long sequence like this, and I want to find the subsequence which is a palindrome, longest palindromic subsequence. It's a classic standard problem. So here is the thing. What is the longest palindromic subsequence of this? I mean, just one, right? The length is just one. Any single or, right? Or no, is it right? Yeah, just one here, right? What about here? What's the longest palindromic? So what is the subsequence? I am allowed to drop some guys, right? So what is the longest palindromic subsequence here? 4, right? A, C, C, A. Okay? Yeah? Okay. What about here? I don't know, right? We did an algorithm here, right? Yeah? Okay. How will you do it? Recursively. So, okay, I give you this string. Can you come up with a recursion to compute the longest palindromic subsequence? Sorry? Okay, so you say, okay, you try to do the thing from the ends, right? You say, okay, this is a string. Either it if it doesn't contain G, what happens? You just recurse on a smaller problem, right? Okay? Maybe then you say, look, I want to include G. If I want to include G, what should happen? You have to match it, no? If I want a palindromic sequence, if I want to include G, what problem should I recurse on? You have to look for its mate G, right? Otherwise it won't be a palindrome, right? Okay, you say, okay, look, I'm going to look at which mate will you do it with? Well, you might as well pick the earliest G that you can find, right? If there is no G, can I do it? Unless you just want that to be the end of the story, right? Okay, so there are two cases. Either you don't include G, in which case the problem becomes smaller, right? You recurse on a string of length n minus 1, right? If you want to include G, you look at the first G that you want to partner it with, and you then recurse on which problem? What string do you recurse on? This string, right? Okay? Because I matched G to G, then I want a longest palindrome in the middle of this. Okay? Does it make sense or no? Yeah? There are two cases. Yeah? If I decide to take G in my palindromic subsequence, I have to partner it with another G, right? I might as well partner it with the first G from the other side. Yes? Okay, if I do that, then I have to say, okay, I put G and G together, and then I have to recurse on this substring, right? Okay? Agreed? Okay. Okay, what happens if, what are the sub-problems I'll generate if I start with a string of length n? What is the structure of that? Here it's a little bit more complicated, no? I start with a string, either I get a prefix, but in the second case I'm not getting a prefix, right? What am I getting? What is this string? I have to recurse on T to C, right? Okay, that's not a prefix. What is it? It's a substring, not subsequence. There are too many subsequences. It's substring of the thing. What is a substring? That is a contiguous piece of the thing, right? A prefix starts always at the thing and goes to some length, right? Suffix always goes here. What is a substring? It can be in the middle, right? So in this recursion, what I'm generating are substrings of the original strings, right? My problems, if I look at the recursion, I'm getting substrings. How many substrings are there of a string of length n? N square, no, and choose 2, right, or something a little, right? You know that I choose this index and I choose that index which is bigger than that, right? The number of substrings is only roughly n square, okay? Okay, this is a tricky one. This is also, in some sense, a straightforward recursion, but it's a little bit more tricky to observe that the sub-problems you are generating are actually polynomial size because they are substrings. Okay? Here too, the recursion is not hard, you have to think, it's a little not obvious, but you think, but the trick is to understand what is the structure of the sub-problems. And if you think for a little bit, you'll realize that there are substrings, and there are not too many substrings. Okay? Alright? So that again, it's the same type of thing. Okay, we come up with a simple recursion, but a little bit harder to understand what the sub-problem structure is. Okay? Okay. That's the template, right? We come up with a recursive algorithm. Now you have to understand the structure of this sub-problems. Otherwise, you can't figure out how many there are. Okay? Okay. And then you memoize the recursion, you make it optimize it, iterate, all that stuff is not too hard. Then you can analyze the time and space. But now I'm going to go to a slightly non-trivial aspect of coming up with a recursion. Okay, this is where dynamic programming gets a little trickier. Okay, Here is a knapsack problem, and I'm going to again come up with a simple problem, but then we'll see more complicated versions of that. So most of you have probably heard of knapsack problem, or maybe if not, but it's a very simple problem. What is the problem? So I have basically a knapsack of some capacity, right? Okay. And then I give you n items. Each item has a size, just a number, and a profit. Okay, another number, all non-negative, right? So maybe I call profit, but let me call it. It has a weight because of thing of knapsack. The capacity of the knapsack is some. It can carry big W pounds, or we are in the US, right? Otherwise we'll have to say kg, right? And n objects, and ith object has a weight Wi and a value Vi, or a profit. Think of it as, right? And you want to fill the knapsack. You can't exceed the capacity of the knapsack, but you want to maximize your profit. Okay. If all the profits are 1, what is the solution? Huh? No. Why is it n? Right. If all the items are the same profit, what do you do? Sorry? Yeah, you pick the smallest weight guys till you finish. You can't take any more. Yeah? A greedy algorithm will give you the right solution, right? If all of them are the same thing, why should I take a bigger weight item compared to a smaller weight item? Right? I don't have to, right? Yeah? Okay, but if the weights are, profits are different, this is not an easy problem. This becomes actually NP-hard. Okay, it's an NP-hard problem, but we'll actually come up with an algorithm, so there is some catch to this, right? So what is the catch we'll figure out later. Okay? Sorry? No, here no, that's not the catch. You'll see, right? All the weights are, all the numbers are integers. Don't worry about that. That's not the, right? Okay. Okay. It's a very basic problem, right? You can see, like, it seems like the most obvious problem, right? In optimization, and it comes up in many subroutine. It's a fundamental problem in geometry, in many, in linear programming and integer programming and so. But here is an example. I have different values and different weights, and my capacity is 11, and it's not obvious. Once you have different values and different weights, the most obvious, if you try greedy algorithms, they fail, okay? And it's not easy to solve this problem, and it's actually a tricky one, okay? Okay, we'll skip the example. And the greedy algorithms, you can see, don't work. Here is a way to try to solve it recursively. Well, one thing you can do is brute force, right? You try all possible subsets and find the one which is the maximum, which satisfies the capacity. That will take 2 to the n time. Well, let's try to see if we can come up with a recursive algorithm for this problem. Okay? How would we recurse, right? You see, the natural thing, you could try is the following, right? So I have n items. Let's order them somehow 1 to n. Either I include the last guy in my solution, or I don't include it, right? If I don't include it, what should I do? I have to recurse on the first n guys, right? N minus 1 guys, right? Okay, but if I include the last guy, what should I do? Weight reduces, right? Okay. So then you see, if you try to write the recursion, what happens? In the first case, we recursed on a problem with only the number of items going down. In the second case, we had to do something else. What is the something else? We had to recurse on a knapsack with smaller capacity, right? Because if I include my last guy, I don't have the same space as the full capacity. If I don't take it into account, I won't get the right solution, right? Okay? Okay, so you see, if you try to write the recursion for this, you realize that in one case, you are getting a sub-problem which involves only the number of items going down, right? In the other case, you are getting a sub-problem where the number of items is going down as well as the size of the knapsack. Okay? So you cannot do the recursion without having the size of the knapsack as something that is part of the recursion. Okay. So you cannot decompose this problem by just thinking of the number of items. You also have to think of the capacity of the knapsack as somehow fundamental to implementing a recursion for this. Okay. That's why this is a little tricky. And so how do we take this into account? We have to introduce this what's called oh, wait a second. So we have to introduce the size of the knapsack into the recursion. So here is what we can do. I mean, I'll define opt of IW to the optimal way of picking items from 1 to I with the total weight not exceeding small w. Okay. Let me define that as a recursive subproblem. Okay. Then I can write a recursion now, right? Opt of IW is what? It is 0 if I equal to 0. There are no items, it is 0, right? If there are two cases. One is, I mean, ignore this case for now. One is, I don't want to include the ith item. Then what is the optimal solution? Opt of I minus 1 W, right? If I want to include the ith guy, what do? I get a profit of Vi, but then the knapsack capacity has to be reduced, right? Okay, so to write the recursion, I couldn't write the recursion without introducing this additional variable which kept track of the capacity of the knapsack. Okay, I was forced to add this additional variable into my recursion. Right? This was not true for edit distance or the palindromic subsequence, right? We could write a simple recursion without doing anything else. We just recursed on sub-problems which are just the same as the original problem. When we tried to solve the knapsack problem, we had to introduce this additional variable, right, which is the capacity of the knapsack. Why? Because we couldn't decompose the problem without doing that. Right? To even write the recursion, we couldn't figure out how to write the recursion without doing that. If you do that, then we get a nice recursion. And then it's obvious, right, from the way we wrote it, what is the number of sub-problems if we start with the knapsack of size n and capacity w. What is it? Well, from the syntax, it is of the form opt I small w, right? How many of them are there? The first parameter is of size, how many things are there? N, and the second parameter is capital W, right? For every size I and every capacity W between, small w between 1 and capital W, I have a different problem that I have to solve, right? So there are n times capital W different problems, right? Right? Okay. So once I have that, it's easy to compute these things, right? I understand the structure of the thing, right? But what is different from this, for this problem from the previous problem? This key idea of introducing this variable, right? So why did we introduce a variable? Because it was not naturally decomposing, right? And we'll dwell on that, but if you have the structure of the subproblems, then you can compute them again by, it's a two-dimensional array, right? Now it is n and w, and you can do it in many ways, right? Row order or column order or topological sort of this dependency graph. However we want to do it, you can do it, right? And then you'll get an algorithm whose running time is what? N times w, right? Okay. Is that a polynomial time algorithm? I said it's NP-hard. Somehow we got a polynomial time algorithm, right? What is the running time of this algorithm? It depends on the number of sub-problems, which is n times w, right? Okay, this is not a polynomial time algorithm. Okay, why is it not a polynomial time algorithm? Because what is the size of the input? If I give you a knapsack instance, what should I write down? What will I tell you? I'll say, here is the input. What do I write down for you? I say W, right? How do I write down W? Say I write down 10,000. Okay? How many bits does it take to write down 10,000? How many digits? Only log of W, right? So it only takes 5 digits to write 10,000, right? And then I say, okay, item 1. value is 2000, weight is 50, item 2, something, right? What is the running time of this algorithm? It is n times w, not n times log w, which is the size of the input, right? N times w. Suppose my knapsack size is 3 billion, okay? The running time of this algorithm will be 3 billion, right? Not log of 3 billion, because I can write 3 billion very easily, right? It only takes roughly 10 digits, right? But the algorithm is going to take 3 billion times n. Okay, so when numbers are involved, right, you have to be very careful. The running time here is depending on not the log of the number of digits to write down this number, but actually on the number itself. Okay, so it's an issue that you should pay attention to, right? And it's called what is called a pseudo polynomial time algorithm, right? Because its running time is polynomial if I take the numbers and write them in unary. But we don't write numbers in unary, right? We write them in binary simply because if you want to write 3 billion in unary, it'll take a long while, right? Okay, so this actually is an NP-hard problem when W is large. Okay, so it's a crazy problem. We'll see later on why that is the case. But I want us to remember the important aspect of this dynamic program as opposed to the edit distance dynamic program. That is, how do you figure out that I have to introduce this new variable for the size of the knapsack capacity? How do you figure that out? Okay? And the idea is that, the basic thing you try to do is you try to split the problem in the natural way. Okay? If I try to split the knapsack problem in the natural way, what should you do? You say, okay, look, maybe I'll take these items, recursively solve them, and take these items and recursively solve them. But then you can't solve them and put their solutions together. Why? Because they share the knapsack capacity, right? Yeah? So the only way to decompose the problem is that if I want to take these guys and fill them in a knapsack and these guys and put them in the knapsack, I have to figure out how much space you're going to give to these guys and how much space you're going to give to this guy. Okay? If you don't do that, then there is no way to decompose the problem, right? So that, whatever is the dependence between the problems when you try to decompose, if you divide and conquer is a possibility where you can decompose without worrying about the dependence because there is no dependence. Okay? But when you cannot decompose a problem, there's a dependence between them, the way to get a recursion is to say, aha, the only way I can get a recursion is if I put the dependence into the recursion itself. I'm not solving the original problem, I'm trying to solve a bigger problem. What is the more general problem? I'm trying to solve a problem where I have not only items but also the knapsack capacity as a variable now. Right? So that should guide you towards what is the additional variables that you need to put into the recursion so that you can get a recursion. Right? Otherwise you won't even get a recursive algorithm for the problem. Okay? That is actually one of the hardest part in dynamic programming, figuring out these additional variables to introduce so that the problem decomposes. Okay? Edit distance and the palindromes don't highlight that aspect, right? But knapsack already shows you that you cannot write a recursion unless you introduce this additional variable. Okay? The key is to figure out which variables and why and when you can actually introduce these variables to create a decomposition. Okay? That's the thing that we want to get to in this class rather than, dynamic programming is, yes, it is recursion which you can memoize, right? The first skill is understanding the structure of the subproblems, right? That is already somewhat non-trivial, right? With palindromic subsequence, it is not as obvious, right, as with edit distance. With knapsack, the problem is different. How do you decompose it? Okay? All right? Any questions? I know for some of you it's a review, it's been there, you've seen this stuff before, but we'll see more advanced examples next lecture. Okay? Okay.
The solution for homework 0 be uploaded?
Yes, yeah, in a day or two.
In a day or two?
Yeah.
Is it usual, like every...
Yes.
Oh, okay.